All right, we are starting chapter 9, which is going to be pretty different than what we've done up to this point. And we're just going to get started with these day 1 notes. So day 1, just so you know, in case this got cut off from your packet, is the first page front and back and a little bit the next page. All right, so we're looking at sequences to begin. A sequence is a function whose domain is the set of positive integers. The numbers a sub 1, a sub 2, a sub 3, all the way to a sub n are the terms of a sequence, and a sub n is the nth term, which will always be some sort of formula, which denotes the sequence. So if you're asked to find the nth term or find a sub n, we're asking you to come up with a formula like this. So this is what a sequence would look like. A sub n equals 3 plus negative 1 to the n power. I want to write the first 3 terms of the sequence. So the first 3 terms is just plug in n equals 1, n equals 2, and n equals 3, and then see what you get for each of those values. So I don't really have a lot of work to show for this one. If I plug in 1, you get 3 plus negative 1, which is 2. Put a comma. If you plug in 2, you get 3 plus 1, which is 4, comma. You put in a 3, 3 minus 1, 2, comma, and then you just do dot, dot, dot to show this sequence can go on forever. And I can tell here it's just going to be 2, 4, 2, 4, 2, 4, et cetera, et cetera. All right. For the next sequence, b sub n, it's n over 1 minus 2n. We're still just plugging in n equals 1, 2, and 3. So if I plug in 1, now maybe I'll do some work here. If I plug in 1, I get 1 minus 2, so I get negative 1. I'm going to do the work, and then I'll write out my official terms here. If I plug in 2, I get 2 over 1 minus 2 times 2 is 4. That's negative 2/3. If I plug in 3, I get 3 over 1 minus 6, negative 3/5. Looks like these terms are decreasing, well, decreasing numerically, but they're negative, so I guess technically they're increasing. Anyway, so the sequence b sub n is equal to negative 1, comma, negative 2/3, comma, negative 3/5, comma, and it would go on forever. One last example. The sequence can be anything. Whatever the formula says, you're plugging in for n. So again, I think I'll just show some math here. So if I plug in 1, I get 1 over 2 minus 1. 1. If I plug in 2, I get 2 squared is 4 over 2 to the second, which is also 4 minus 1, 4/3. That's increasing so far. If I plug in 3, 3 squared is 9. Over 2 to the third is 8 minus 1, 9/7. Okay, I believe this sequence is going to maybe start off increasing and then decrease if I were to keep going, because my numbers would get closer together. All right, so c sub n is equal to 1, and then 4/3, 9/7, dot, dot, dot. So listing out terms of a sequence, easy. Is that likely to be on the AP test? No, but it's where we have to start. Okay, a series can be recursively defined. A series can be recursively defined if you're given one or more of the first few terms, and all other terms are defined using the previous terms. So here's an example. They'll give you the first term, d sub 1 is 25, that's the first term. And then it says every term after that, d sub n plus 1, is equal to the previous term, d sub n, minus 5. So the next term is equal to the previous term minus 5. So if d1 is 25, then d2 should be d1 minus 5, so 20. d3 should be d2 minus 5, which is 15, et cetera, et cetera. So it's so d sub n is 25, 20, 15, that's a Some terminology from last chapter. A sequence converges if the terms approach a limiting value. If the limit as n approaches infinity of a sub n exists, then the sequence converges. If the limit of a sequence does not exist, so it approaches infinity or negative infinity, then the sequence diverges. And converge and diverge mean the same thing. Converge means that the terms are approaching a finite number. In chapter 8, we were saying the area approaches a finite number. Here, it's just these numerical terms are going to stop at a certain value or get very close to it, I should say. Diverge means that the sequence does not reach a limiting value. So like these terms, for example, diverge because they could decrease without end. There's nothing that says this has to stop at 0 or negative 50 or whatever. All right, so here's the theorem. Let L be a real number. Let f be a function of a real value such that the limit as x approaches infinity of f of x equals L. So what is that saying? Let's do a little picture here. That's just saying, here's some f of x. I'm going to just draw in a boring little f of x. Say that's f of x. And let's just say L is some y value here. So this is just saying, hey, f of x, as we go toward infinity, it's approaching L. So that is the limit as x approaches infinity. If a sub n is a sequence such that f of n equals a sub n for every positive integer of n, then the limit as n approaches infinity of a sub n is also equal to L. All that's saying is a sub n, since they're only integer values, let's go back to our sequences for a minute. It would just be a series of disconnected points at whatever the numerical values are. So if the terms in the sequence are equal to the values of the function at integer values, so like at 1, we're here, at 2, we're here, et cetera, et cetera. So if these dots represent a sub n, then those terms are also going to be approaching that same L, that same limiting value. So basically, this theorem just gives us a green light to use our regular limit rules to figure out limits of sequences. So what do I mean by regular limit rules? Well, we're talking about limits at infinity, so horizontal asymptotes, L'Hopital's, that kind of thing. So find the limit in order to determine convergence or divergence. Remember, if we get a number, we have convergence. We get infinity or negative infinity, divergence. All right, so here's the sequence a sub n. Instead of generating a bunch of terms, I want to look at the limit as n approaches infinity of n plus 1 over n. This is x plus 1 over x. If it were that function, we would say, oh, there's a horizontal asymptote, and this is a tie. And so the horizontal asymptote is 1. You're still doing the same thing. These terms, as you get out really large, infinity plus 1 is not very different than infinity. So it's going to come out to 1. Since I got a numerical value, I can say a sub n, the sequence, converges. What does it converge to? It converges to 1. And remember, all that means is the terms in a sub n, if I were to write these out, say I write out a million terms, the terms approach 1. They're not going to start off at 1. They're going to start off at 2, actually, right? If you plug in 1, you get 2. Then if you plug in 3, you get, or 3. If you plug in 2, you get 3 over 2, 1.5. So it decreased. Plug in 3, you get 4 over 3, 1 1/3. So they are going to slowly get back to 1 as you start plugging in huge numbers. What about the next one? The limits as n approaches infinity of 1 plus 3 over n to the n divided by 4 power. This kind of looks like an interest formula, right? Remember we talked about this in chapter 8? This is one of those blank and be done problems. Equal to e to the ab, but you have to be careful. A is the numerator, that's fine. B is the number being multiplied by n. So the fact that it's divided by 4 means this is e to the 3 times 1/4, or in other words, e to the 3/4. The fact that I got a number means that the sequence b sub n converges. to e to the 3/4. In other words, the terms, as you start plugging in huge numbers for infinity, they're going to practically be e to the 3/4. That's the value they approach. The limit as n approaches infinity of 1 over n squared. This is a bottom heavy. Think of it as a rational function. It's bottom heavy. 1 over infinity is 0. Again, that's a number. So c sub n converges to 0. The terms approach 0. On to the next page. What about my next one? We're still doing the same thing. The limit as equals there. The limit as n approaches infinity of 3 plus -1 to the n power. Well, the limit as n approaches infinity of 3 is still 3. But then depending on whether n is positive or negative, you're going to get plus or minus 1. So this is that 2, 4, 2, 4. There is no limiting value. That's always going to bounce back and forth between 2 and 4. So d sub n diverges. So I know I didn't get infinity or negative infinity, but it's not zeroing in on a value. Convergence means you're zeroing in on one single number. All right, so let's write that down. So terms never approach a single value. The limit as n approaches infinity of n over 1 minus 2 to the n. That's rational, tie. The coefficients divide out to -1/2. Therefore, e sub n converges to -1/2. You're allowed to get negatives, positives, 0, whatever. It just means these terms eventually will approach -1/2. Now, what about this one? We're going to get, if we plug in infinity, we're going to get infinity over infinity. So we are going to use L'Hopital's. In some cases, we aren't going to be able, we're going to have something we can't take a derivative of. So you are allowed to think about function races without formally doing L'Hopital's. I know that this is going to come out to 0 because an exponential function will always grow faster than any polynomial, even if this is n to the 1/1,000,000th power. As we get far enough out in our direction of infinity, 2 to the n is going to beat n to the 1/1,000,000th in the long run. Okay, so I know that this is technically bottom heavy. You can kind of think of it that way. I know the limit's 0, but I have to formally show it. And I'll do something like this. I will show that the limit as n approaches infinity of n squared is infinity. That's also the limit as n approaches infinity of 2 to the n minus 1. Use L'Hopital's. L'Hopital says we're allowed to say the limit as n approaches infinity of the derivative of n squared, which is 2n, over the derivative of 2 to the n minus 1. What's the derivative of an exponential? It's 2 to the n times the natural log of the base, natural log of, and the 1 goes away. Now that's still infinity over infinity. In interest of time, I'm just going to say, okay, use L'Hopital's again, but technically you'd have to write out something like this. Take another derivative, and you'll get to 2 over, again, the derivative of 2 to the n is 2 to the n. Natural log of 2 is a constant, but you're going to have another times natural log 2, so natural log 2 will become squared in the denominator. It's just a constant value. 2 over infinity is 0. Therefore, sequence f sub n converges to 0. So function races are supposed to help you in your head kind of look ahead and think, okay, what should the answer be? And then how do I show it? This is still not official enough for free response. I'm just shortening things in interest of time. Some limit properties that are kind of basic. Just let's say that the limit as n approaches infinity of sequence a sub n equals L, and the limit at infinity of sequence b is equal to k. You are, just like with functions, you are allowed to add and subtract limits together. So this will be L plus or minus k. You are allowed to multiply limits together. Remember, it's integrals that we can't multiply together. This area times this area is not going to work out. But just with numerical limits, we can. If we have a constant where c is just some real number, then the limit of the constant times your sequence will be the constant times whatever the limit value is. And we can also divide limits, provided that the denominator is not equal to 0. Okay, factorials. They're going to pop up a reasonable amount in this chapter. So what are factorials again? Denoted by an exclamation point. So n factorial is n exclamation point. It is in your calculator if you ever need to figure out a factorial. If I want 4 factorial, math, probability, right there. 4 factorial is 24. Factorial means take whatever your number is and multiply it by every integer previous to that. So I know it's written out as 1 times 3 times 1 times 2 times 3 times 4 times whatever, all the way up to n. I think of it in the reverse order. So I think 4 factorial is 4 times 3 times 2. 0 factorial is equal to 1. We're not going to do a proof of that, but it has to be true so that everything works out for us. But there is a proof for why that's true. Factorials grow faster than any other exponentials. So again, function races. We don't have a rule for derivatives of factorials. So we do need to rely on function races here. The fastest growing function that we have is factorials. Factorials will always grow faster than exponentials, so they're now bumped to second place. And then after exponentials are our polynomials, like x squared, x to the third, whatever. And then coming in fourth place would be our natural log functions. Those grow nice and slow. Okay. In chapter 1, we talked about a squeeze theorem. So this is just like it was in chapter 1. If I have an unknown, sequence, like I don't know how my sequence C sub n behaves, but I do know that it is squeezed or sandwiched in between sequences A and B. And if I can figure out the limit of sequence A and the limit of sequence B, and they equal the same thing at some point, then the limit of C is going to match that. So all that's saying is if I know this to be true, I can take the limit as n approaches infinity of each of these terms, and I can squeeze the limit as n approaches infinity of C. I can squeeze it in between A and B. All right, so what am I talking about? So here's an example. Show that the sequence A sub n, which is equal to -1 to the n over n factorial, converges and find its limit. So I want to think about what can I squeeze it in between? We're talking about at infinity. So it's actually not true for small values of n, like 1, 2, maybe even 3, that 1 over n factorial, -1 to the n over n factorial is not necessarily always less than or equal to 1 over 2 to the n. For initial values, like plug in 1 and 2, you're going to get like 1/2 is not less than or equal to 1/4, for example. But as we start getting out to large numbers of n factorial will be larger than 2 to the n. If I have a larger denominator, I have a smaller overall fraction. Okay, so for large values of n, this fraction is less than or equal to this fraction. Now this fraction is bigger than -1 over 2 to the n. Again, for large values of n, because 1 over n factorial could be something positive, and that would be bigger than the negative version of -1 over 2 to the n. Why did I pick that? Because I know the limit as n approaches infinity of -1 over 2 to the n That can tell me about the limit as n approaches infinity of -1 to the n over n factorial, and that can tell me what I know about n, the limit as n approaches infinity of +1 over 2 to the n. The limits on the end are both 0. Those are bottom heavy. 1 divided by infinity, -1 divided by infinity. We are sandwiched between 0. So by the squeeze theorem, my limit at infinity has to equal 0 as well. It has to be between 0 and 0. All right, so therefore, the limit as n approaches infinity of, I'm just going to write a sub n, is equal to 0 as well. That's just by that squeeze theorem. All right, this one gets used a lot, the absolute value theorem for sequences. So if the limit as n approaches infinity of the absolute value of a sequence equals 0, then the limit as n approaches infinity of just the sequence itself without forcing every term to be positive is also 0. What is this used for? This is mostly used if I have terms that alternate. So maybe I have one of those -1 to the n sequences and it starts out positive and then it goes negative. But as I go on, the positive and negatives get closer and closer to 0. So visually I can see that, yeah, this is converging and approaching 0. But all we're saying is to verify that, why don't we just swing all the negative terms, take the absolute value of them and force them to be positive? So like this guy would still be up here. This one swings up to here. This one stays. Doing kind of a poor job sketching this. But if all of those terms, if you make all of the distances from 0 positive, you can see visually that, oh yeah, that's approaching 0. So just because they're alternating doesn't mean that they're not getting smaller and smaller. They're also approaching 0. There's not much difference between positive, 1 times 10 to the -50th and negative 1 times 10 to the -50th. They're both practically 0. All right. Now this next part can be kind of hard. Trying to come up with the actual sequence, coming up with a formula. I want to find a sequence whose first 5 terms are these, and then I want to determine whether that sequence converges or diverges. Now, it could be that we get different formulas. As long as they work for all 5 terms or all terms that are given to you, then it's okay. So here's how I do this. I show myself, I have to visually see it, what the n value is for each term. So first term, second, third, fourth, and fifth. And basically, you're coming up with 2 little formulas. Give yourself a formula for the numerator and one for the denominator. And it's kind of just whatever pattern you see that works for all of them. So I'm looking at the numerator first. 2, 4, 8, 16, 32. Those are all powers of 2. And if I say 2 to the n, that matches up, right? 2 to the third, 2 to the fourth, 2 to the fifth. So the numerator is 2 to the n. What about the denominator? You're comparing 1 to 1, 2 to 3, 3 to 5, 4 to 7, 5 to 9. They can be harder to come up with. I'm noticing, especially as I get out here, 5 times 2 is 10, I'm 1 off. 4 times 2 is 8, I'm 1 off. 3 times 2 is 6, 1 off. 4, 1 off. 2, 1 off. So if I do 2 times n minus 1, that should give me every term for the denominator. You have to check all given terms. You don't have the right formula if it works for 4 out of the 5 terms, for example. Okay, so this is a sub n. Now that I have a sub n, I want to say, well, what is the limit as n approaches infinity of 2 to the n over 2n minus 1? Now, I should do L'Hopital's rule because technically this is infinity over infinity, but think about function races. Basically, this is big infinity over little infinity. Or if I do a round of L'Hopital's, I'm going to get 2 to the n natural log of 2 over 2. So I know it's going to come out to infinity. We should do this more formally on an AP test if it's free response. But a lot of these are going to be multiple choice, so it's good to just think about it kind of logically. Anyway, therefore, they didn't really call this a sub n in the problem, so I'm just going to call it the sequence. The sequence diverges. These terms are just going to keep growing and getting bigger and bigger. You can also look at them in their decimal form if that kind of helps you. They're not going to, even though they might decrease at first, they're ultimately going to increase and never end. Okay, last problem. Determine an nth term. Remember, that just means come up with the formula for a sub n. I got that in the beginning of the notes. For a sequence whose first 5 terms are these. And determine convergence or divergence. So again, I pretty much have to write the numbers for myself. I'm just kind of visual that way. And I'm trying to come up with the nth term. So formula for the numerator, a formula for the denominator. Now this might not be obvious right away, although I will say if you have to come up with a sequence, which is not super common on the AP test, but if you do, common things to look for are the factorials or powers of 2 or 3 and compare them to what you have. So 1 factorial is 1, 2 factorial is 2, 3 times 2 times 1 is 6, 4 times 3 times 2 times 1 is 24. You're going to memorize these eventually. 5 times 4 times 3 times 2 times 1 is 120, or again, 5 times 24, 120. So the denominator is n factorial. Sometimes you'll see that it's like, if these were all knocked back one, it would be like n plus 1 factorial. What about the numerator? Like I said, common things are powers of 2, powers of 3. All of these are close to powers of 3, right? But they're just one off. Like normally we would have 3, 9, 27, 81, 243. So they're all 3 to the n, but then you subtract 1 from that. And then how do I get the alternating negative signs? Well, all of the odds are negative terms. So if I just multiply in a -1 to the n, I would make all the odd terms negative and all the even terms positive. And if it were the other way around, I could say like -1 to the n plus 1 or -1 or whatever. N plus 1 is usually safer, by the way. And that would force all the odds to be even powers and all the evens to be odd powers. Okay, so I have this. Now this is an alternating sequence, right? So I should use that theorem at the top of the page. It says, well, let's look at the absolute value. As n approaches infinity, let's look at the absolute value of our sequence. All that means is when you're taking the limit, you just leave out the -1 to the n part. That's the alternating piece. If that weren't there, all of these terms would be 3 to the n minus 1 over n factorial. So just look at this. And again, I kind of have to do function races here because if I wanted to do L'Hopital's, I don't know what the derivative of a factorial is, right? So this is equal to a smaller infinity over a bigger infinity because factorials will grow more quickly than exponentials, no matter what the base in the long run. So that didn't show much difference between those, sorry. So that ultimately will come out to 0. Since we know the limit as n approaches infinity of the absolute value of a sub n equals 0, therefore the limit as n approaches infinity of a sub n will equal 0 as well. That theorem only works for 0. So if you had an alternating sequence and the sequence absolute value, the limit was like 5, it doesn't mean that the alternating limit is 5. So this only is true if we get 0 here. If we get something other than 0, that's kind of what we'll be investigating in later chapters or in later sections of this chapter. Okay, that's it for today. Your homework is assignment number 9.